Thank you, everyone, for your patience as we get these technical issues worked out. Today, we're going to hear about the PISTON field campaign as presented by Professor Jim Moum from Oregon State University. Jim received his PhD in physics from the University of British Columbia. He is a physical oceanographer who works on studying ocean physics, especially upper ocean physics, throughout the globe, but also with a focus on tropics and also considering the ocean feedbacks to the atmosphere. Sue Chen is a meteorologist at the Naval Research Laboratory. Sue and I overlapped in our graduate training for a little while at Colorado State University, where she earned her master's degree, and then she went on to earn her PhD in meteorology from the Naval Postgraduate School. And so she does a lot of work with modeling of the ocean atmosphere system. So today we're going to be hearing from an oceanographer and an atmospheric scientist. And I think they may be talking about the coupled processes in the ocean and atmosphere. So thank you both, Jim and Sue, and I will turn it back over to you.
Okay, thanks, Charlotte. So we were asked here to give a brief presentation on PISTON, which is an acronym for Propagation of Inter-Seasonal Tropical Oscillations. It was a planned land-air-sea experiment by the Marine Meteorology Program at the Office of Naval Research. They've been trying to do a land-air-sea experiment for at least the last decade. 10 years ago, they threw their support behind Dynamo. They were one of the early funders of Dynamo and turned a land-air-sea experiment into a major contribution to Dynamo. PISTON was the next version of the land-air-sea experiment. And it's an example of a carefully planned campaign that was re-engineered on the fly, and I'll tell you why. Next slide, please. So in order to do an experiment within the exclusive economic zone of any country, a marine scientific research clearance is required under the UN Conventional Law of the Sea in order to make measurements either within the EEZ or over the continental shelf of a sovereign nation. That was denied in 2018 for the PISTON campaign. Following the 2018 experiment, we planned for a 2019 campaign to overlap with the CAMPEX experiment, which is a NASA-funded experiment on clouds, aerosols, and monsoon processes to take place off the west coast of Luzon. And we filed a new request to do research there. That was again denied in 2019. And I have to say that this was due to political things well above our pay grade. And we got tremendous amount of support from people in the State Department and from our Filipino colleagues to help get this MSR through in both 2018 and 2019. And the denials were unexpected. The result was the land came out of the land-air-sea interaction experiment, and this became an air-sea interaction experiment. Next slide, please. So in 2018, things were late developing. Denial would happen at the last minute. We had oceanographic moorings planned for the west coast of Luzon that had been shipped. And we heard no word from the Philippines Department of Foreign Affairs about our MSR. And we had to change plans on the fly. A planned mooring deployment cruise in May 2018 was canceled because we had no place to put the moorings. In June 2018, with a planned experiment in August 2018, we had to plan on going into international waters and replan the deployment locations and reconfigure the experiment. This is the operating conditions during 2018. In the upper left-hand corner, you can see the operating area for PISTON. Within that region were deployed 2 moorings. The colored tracks are tracks of tropical cyclones. And you can see some of the variables on the right-hand column. And at the bottom, you can see a list of measurements that were made during that experiment. And there are cruise reports and metadata available on the data sharing site now. While we were at sea, so this is we spent almost 60 days at sea in 2018 and another 3 weeks in 2019. During this time, we benefited from daily detailed weather forecasts prepared by a forecast team of mostly students, but led by Michael Bell at Colorado State. Next slide, please. In 2019, the NASA CAMPEX campaign, which had been canceled in, you know what? We missed the slide. Let's go back a few. Back. There we go. So here, we missed the slide here. This is our 47-page science plan for a land-air-sea experiment off the west coast of Luzon to study the BSISO. It was coordinated with atmospheric scientists from the Philippine Met Agency and ocean scientists from the University of the Philippines, and included sounding and radar sites from Luzon and coordination with research vessels in the Philippines. And it was planned to be a collaboration with the aircraft-based NASA CAMPEX campaign in 2018, which was canceled due to aircraft readiness in 2018. So that didn't occur, and at the same time, we got the denial of the MSR. Okay, let's go back to where we were. 2019, there we go, up one. So in 2019, we went out, up one, other way, back three. There we go. Okay, in which we, so the CAMPEX campaign included aircraft flights from the two aircraft operating out of Clark Air Base, and our mission as a ship was to maintain position within aircraft range. So our operating range was northeast of Luzon, and we got a number of aircraft flights over the region of the ship, and we had continuous feedback with the CAMPEX campaign during that 3-week at-sea period. And some of the conditions and the measurements are shown there on the right. Next slide. 2018, we operated off the RV Thompson. And by the way, Elizabeth Thompson from NOAA ESRL made these couple of nice slides to represent the measurements made during these campaigns. I won't list all these right now. Next slide. In 2019, we operated off of the RV Sally Ride out of Scripps. The Thompson is out of the University of Washington, making very similar sets of measurements, very comprehensive. And what you can see on the upper right-hand corner is the ship departing Keelung Harbor in early September or late August 2019, with the C-band radar dome, the C-pole, mounted on a container van ahead of the bridge. Part of the preparation for this experiment required figuring out how to mount the C-pole radar so that the ship's company would be in agreement. You can see that this blocks the view from the bridge. So we made provisions very early on to make accommodations for the mounting of that radar. During Dynamo, that radar dome was mounted up on top of the main mast and had a very clear view around it, and was out of the way of obstructing the view of the bridge. Down one. Next slide, please. So the continuous, in the end, to summarize the measurements, they represent continuous profiling measurements from 600 meters beneath the sea surface to 27 kilometers above the sea surface, including the 8 per day soundings, and looking out from the ship 120 kilometers via the C-pole radar. Next slide. One way to look at this is with this great movie that Kyle Chudler, who's a student working with Steve Rutledge at CSU, made is a movie that shows the location of the ship in that small circle with the X on it, which shows precipitation estimates from the Seapole radar, superimposed on a large-scale estimate of IMERG precipitation from reanalysis product, pressure contours, and surface wind vectors. And if you, yeah, there we go. If you start that movie, you can see the progression of two TCs during the time we're moving into the area. And we made continuous measurements. You can see the difference between the reanalysis product and the detailed measurements of rainfall from the Seapole. We did a dual Doppler exercise. That's what we're doing right now with RV Mirai, which had a C-band radar on it. And we watched the progression of large-scale MCSs come through. Can you stop it for a sec there? Stop the movie. This is the passage through here of Typhoon Jebi. And this is very interesting. Move it forward now. It's moving into the area, and you can see the surface wind vectors around Jebi, and you can see it coming up in the bottom left-hand corner. You can see a progression of deep convection and wind going into the Indian Ocean across the maritime continent. Hold on, stop. And you can see that continuous interaction between what's happening. It's not quite fully developed yet between the extension of the monsoon in the Indian Ocean and the super typhoon Jebi as it propagates now northwards as well as slightly westwards. Continue. No, next, back one. Continue the movie. There you go. Yeah, stop it there. Or move, no, yeah, I'm sorry. Continue the movie. I think we're at the right place. So here we're still at sea, but we have noticed that there is a super typhoon moving in. And in preparation for this, we deployed a series of profiling floats ahead of this super typhoon Mangkhut, which put a lot of energy into the ocean, extracted a lot of heat energy out of the ocean. And we put these floats in ahead of Mangkhut while we were reprovisioning in Palau. And then we came back out and made measurements behind Mangkhut, which later hit the Philippines pretty hard. Okay, next slide, please. And this is the result of some of the measurements from the profiling floats in the upper ocean. This is a paper that has been published in JGR. 8 profiling floats were put in ahead of the typhoons, 2 of them immediately ahead of the projected path of Mangkhut, and 2 of them were within a couple of kilometers of the eye of the typhoon as far as we can tell. And what we can see in here is the temperature structure in the upper ocean, showing the cold wakes of typhoons Mangkhut and Trami. Eventually, super typhoon U2 propagated into the area, and a map of the cold wakes on the surface shows the extent of the advected cold wakes, the sum of the advected cold wakes of all of these typhoons. U2 was a super typhoon moving into the area a couple of weeks after the cold wakes occurred. And U2 weakened in strength as it propagated over the cold wakes, suggesting the possibility of the reduction in intensity of U2 due to the reduction of heat energy available in the ocean from the previous typhoons. And this was seen in detail from this great set of float measurements that we deployed ahead of Mangkhut. Next slide, please. And right now we are working on not me personally, but people in the PISTON program are working on a background paper looking at a large-scale evolution of the atmosphere and the ocean during the PISTON 2018 experiment. And we had expected to see variability associated with the boreal summer interseasonal oscillation. In effect, what we saw was variability associated with easterly waves, tropical cyclones, and TC-induced interactions with westerly monsoon extensions, and a late suppressed phase MJO event that occurred as well. Next slide, please. Those previous shows the interaction of the TC Jebi with the monsoon extension that we saw in the movie. And this is the structure of the ocean that shows the pre-Mancute state and the post-Mancute state in terms of salinity, temperature, and velocity. And there are several takeaways from this. One is the cooling of the upper ocean associated with the passage of the TCs. Another is the acceleration of near-surface currents. And that has a consequence in a number of ways. And if we go down one, next slide, sorry. We can see the expression in terms of the velocity shear in the upper 400 meters of the ocean. Between 100 meters and 300 meters, before and after the passage of Super Typhoon Mangkhut, we can see an increase in RMS velocity shear of about 40%. So this is a long ways away from the upper ocean mixed layer, and it's associated with the propagation downwards of near inertial gravity waves. And that's what we're seeing on the right side of this picture. Those bands are associated with the near inertial waves. Associated with this is an energization of mixing in that range. So this is below the mixed layer. It's not associated with direct surface forcing. It's associated with indirect forcing, I think, due to downward propagation of the near inertial waves, such that the increase in the turbulence between the pre-cyclone and the post-cyclone state is a factor of 17. So that 40% increase in shear is associated with a almost 20-fold increase in the turbulent dissipation rate. That's a little bit of a puzzle. It seems disproportionate, and it's one of the big challenges of this experiment. Next slide, please. Oh, and we put out these two long-term moorings, and we have these great records from these heavily instrumented moorings, roughly 100 sensors per mooring, including 28 turbulence sensors for the first time. They were recovered with near zero instrument loss, almost a 99% data return, thanks to great engineering from our people at Scripps. And what you can see here is the meridional velocities, and filtered in the third panel down, in terms of the near inertial flows. A detail is shown in figure B, where we can see the meridional flow, and you can see the emphasis on the near inertial wave propagation due to strong forcing events of the surface. We're still working up the turbulence data. This is a very exciting data set. Next slide, please. So a few summary points. The land air-sea experiment turned into an air-sea experiment. It's a smaller version of, and in the same region as Toga Core and Dynamo. We planned for forcing from the BSISO. Both campaigns in 2018 and 2019 were dominated by easterly waves and TC activity and interactions between the TCs and the monsoon extensions. In particular, PISTON featured improved technology and sampling frequencies compared to the Toga Core and Dynamo experiments, which some of us were involved in all three of those. In terms of one, measuring the upper few meters of the ocean, and in particular, the focus on the diurnal warm layer. New insights from that are already appearing. An improved C-band radar, the CPOL from CSU, and the inclusion of the high spectral resolution LiDAR from University of Wisconsin. And in addition, these long-term moored records. So it's a new data set. in the sparsely sampled Western Pacific, which extends from well below the sea surface to the soundings above the sea surface. That data is already being used to test gridded reanalysis products, which are in turn used for many things, including understanding mechanisms controlling convection in the region. The heavily instrumented moorings for piston provide a low latitude analog to a nearly identical high latitude mooring, instrumented very similarly to look near inertial wave propagation in a strong forcing regime in the North Atlantic. So these measurements by themselves are extremely valuable. And next slide, please. And I'll pass this over to Sue Chen to discuss the modeling component.
Thank you, Jim. Jenny, you have to drive it from your side. Okay. Good morning, everyone. I'm glad to represent the modeling group to tell you the up-to-date progress on the piston modeling group. Next slide. Prior to the field campaign, the piston modeling team each reached a consensus of topics to focus on. So it's kind of like showing these two schematic. So the schematic on the top left is produced by Emily Shore of OSU that show these processes, including the BSISO phase, diurnal cycle in precipitation, air-sea airline and land-sea interaction, and focus on west of the Luzon. And so the range of the model experiments that the piston modeling group end up doing is shown on the table on the right. So it breaks down to test hypothesis, model to use, and what type of observation are needed, and the composition of the modeling groups that will run these experiments to test this science hypothesis. The modeling groups include PIs from NRL, CSU, Columbia University, OSU, and then JPL. Hope I'm not missing somebody. Oh, and then NOAA. As you have already heard from Jim, Piston 2018 and 19 field campaign ends up over the east of Luzon, over the Western Pacific, with a minimal land influence. So the modeling result that I will discuss later are skewed, as you will see, toward including the land and then topographic effect. And so the topic that we'll be looking at is intra-seasonal predictability under the MGO monsoon BSISO, a little bit about diurnal cycle and atmosphere land interaction, atmosphere convection, topographic effect, and air-sea interaction during typhoon. Next slide. So this slide shows what the model type that we're using. It includes a global deterministic, couple on couple, global ensemble, again, couple on couple, limited area, prediction, couple on couple, and large area models, simulation model, and the single column models. So the experiment design is either two-way, one-way, couple on couple, real data, or use the idealized initialization. And models, experiments ranging from forecast versus a hindcast. And so for the real-time support for the 2 years field campaign is done by NRL's the limited area couple model COEMS. And so this collage on the right and just to show you a range of model product that COEMS was put out. And also included is a web link that we have a daily forecast summary, kind of summarize what we see in the model out to like 48 hours. So model is around twice a day. And so we have many, as you know, being the research center, trying to run a real-time model, we have our up and downs but we were able to overcome a lot of difficulty and try to provide more kind of detailed mesoscale feature to the ship. And then so most importantly, I hope that's valuable to the ship is that during 2018, we have many typhoon passage. So that created a high wind and sea hazard condition. And so in co-answer, we provide, because it's couple model, so we're able to provide more detailed significant wave height and then the swell direction and peak wave height information and the period to the ship. Next slide. Okay, so I'll start with global model. So the only global model that's within the PISTON PI team is the NRL, a Navy SPC. And so this is, so our team is looking at the sub-X experiments, and this is from January, from June, July, and August 1999 to 2015. And so it's looking at the 3 weeks forecast. And so the top, the A is the observation. This is the OLR anomaly. B is from ESPC. C is the ECNWF, and then D is the CFS version 2. And then so as you can see that all three models were able to produce the classical northwest southeast tilt of the BSI. So, but the amplitude vary quite a bit. ESPC is too strong. ECMWF anomaly are too weak, and CFS version 2 has a lot of mean model biases, just kind of in from the Bay of Bengal all the way to the maritime continent. And 3 panels on the right shows that the when we look at just focus on the ESPC and only focus on the BSSO, and then so to look at the predictability that for the Navy SPC depends on which basin you are, and so they are the predictability for the maritime continent is the best. This is the 17 overall is the 17 days. But if you break down to Indian Ocean and Western Pacific is the worst. It only have 12 days, and we have traced back the problem to the prediction of the typhoon. And so this work done. This is led by my colleague Maria Flatau. And next slide. So this slide is also from our team and led by Matt Jeniga. So he's further drilled down to look at only the 2017 from June to November and look at a lot more models and focus on the equatorial waves. And so the model type is shown on the table on the top, including ESPC, ECNWF, and the 3 model, and the NOAA CFS version 2, and add 2 more Bureau of Meteorology's model and the UKMO model. And so as you can see, they all have a different resolution and different round frequency, and number of the round depending on how many ensemble members they have. And then so this is on the right, it shows that the filter a large scale OLR anomaly of the large scale equatorial waves, and then look at the anomaly correlation. And so what Matt found out is that the NGO prediction actually ECNWF and the Navy SPC is quite good, have a good scale out to week 3. However, that the both the Kelvin wave and the Rossby wave vary quite a bit among the models. And so it looks like that the future work that if you want to increase the predictability of the global model, maybe you should pay more attention to the how the model representation of the equatorial Rossby waves, but the results are just for this case, so need to be looking into further. Next slide. Okay, so to move on to all the mesoscale modeling results. So this slide is provided by the CSU, and RA Drager, and he used idealized REMS setup to study the soil moisture fraction sensitivity on the lane convection co-pool evolution shown in this movie. As you can see that the convection kind of evolution, and you can see this co-pool that represented by the blotches of the blue color. And he found that using a drier soil, the co-pools are much larger and stronger at the early stage, but dissipate early compared with the wet soil run. And also for the wet soil run, he shows that on the right top figure that you have this moisture ring that showed up, but it's absent in the dry soil experiment. Next slide. Okay, and so this is actually two studies that look at the basically the convective and the environment interaction. And so the left one is the done by also by CSU using the REMS. It's led by Benjamin Toms. And so what they were looking at during the MGO phases, and they look at how the evolution of the convection evolved. And what they found is there's anomalous, long-lasting convective cells in the initial phase of the MGO. And then in the intermediate stage, there's an increased number of cells. And at the later stage of the NGO, there will be more expensive cells in the NGO suppressed phase toward the end. So on the right is done by Derek Passat and co-authors from JPL. So they also used REMS, and then they did a 10,000 Monte Carlo simulation to look at the environment factor that control the convection evolution. So the question they asked is showing on the top, and what is the magnitude of the response of convection to the change of the environment, and which environmental factor have the largest influence? That's the sensitivity depends on the convective morphology. And so the two figure here shows the rank histogram. So they look at the suite of low level, mid level, temperature, wind, moisture parameter. And they found that the change to the microphysics scheme in REMS produced a similar same kind of magnitude response in convective hydrological cycle, dynamics, and latent heat, as a change to just look at the initial condition perturbation. And as for the initial condition of perturbation, it seems to have a much larger effect on the radiative fluxes than when do the perturbation to the microphysics scheme. And what they found that the distribution of the low-level latent heating revealed that changing in microphysics scheme have a larger influence on the co-pool properties than changing to the environment. So the dominant effects are produced by a subset of the cloud microphysics and the thermodynamic structure function. And the most influential microphysics are the autoconversion threshold, the rain particle size, the distribution intercept, and the ice particle force speed parameters. So if you want to learn more about detail of these two studies, it's all being published. The references shown on the slide. Next, please. Okay, so this is now move on to a different topic of looking the topographic effect. And this is the work done by Ray Palaf from the Florida Institute of Technology and co-author. And so what they were looking at is during the 2019 April and June event, and this is during the Yasi time period. And so so you see that they're looking at the 3 box of the convection, the detailed momentum budget on those 3 boxes that's behind and in front of Borneo. This is the first box. The second box, this is between Borneo and Silhouette, and box C is behind the Silhouette. And so what they found is that the vertical integrated moisture budget shows the decrease in precipitation when they completely remove the topography from their, this is a WRF simulation. And then the vertical advection increase over the area A and C, but decrease over the area B. Horizontal advection increase over area B, and the process is different in different parts of the maritime continent. So this work is already published, submitted to the GRL. So more detail you can find it there once it's published. Next slide, please. Okay, so this is the second study that look at the topographic effect. Is led by Emily Riley and co-authors. They used the range model and then vary the terrain height over by the Luzon. As you can see from the left top, they did a flat terrain run and then 2 times the topography terrain run, and focus on the Luzon area. And they found that the diurnal sea breeze is much deeper and stronger in the run with the topography. So the magnitude of the topography really dictate the timing, intensity, and location of the diurnal precipitation. Next, please. Okay, so this is a study, again, by the NRL team, PISTON team. So this is the study is actually look at both the air-ocean, air-land, and the air-sea interaction. So what we did is, in collaboration with Julie Poland and Olive Cabrera, and so we were looking at all the Philippines discharge in this region into the coastal ocean. And so you can see that on the right top, that shows the number of rivers in this over the South China Sea. Actually, it's quite a few, ranging from a small to a very large river, such as Mekong River in Vietnam, and the total numbers is approaching like 80. And so Philippines has the most number of rivers, it's about 40. And so we did a 3-model sensitivity experiment, and fortunately, there were some measurements from the Philippines on the west coast of Luzon. So we were able to look at both the atmosphere and the ocean response. So in the middle panel here shows that the top is the Cohen's sensitivity experiment, where we call the realistic round, because comparing with the work done by Julie and Olive, that they found that actually the climatology river discharge database that COAM uses is too low for this region. And so they kind of boosted up using the 1 standard deviation and increased the amount during the summer season. And so compare with the observation, you can see the climatology, the original climatology is in the bottom figure. And so this is the salinity vertical structure in the zonal direction. So you can see that once we included much more discharge of the fresh water from land, the model is able to represent more closely to the observation. But of course, you see that that model is still too much, too salient compared to the observation to the east of the coast toward the center of the South China Sea. So we suspect that maybe the climatology value for other river is also too low. And so, so now move to the left panel, and then we look at the diurnal response. And so this is during the BSISO event, and so by just changing the river discharge, that we can actually shift both the land and ocean diurnal cycle timing. And so what we found is that the start time of the ocean precipitation convection is started a few hours much earlier, and as effect that the land is later because the upward motion from the ocean convection actually suppress the land convection and then delay the onset of the convection. Next slide. Okay, so this is the work done by Xiaoguang Wang and Adam Sobel and co-authors. And so they were using coupled WRF model with HICOM to look at the air-sea interaction during Typhoon Mengka. And this is one of the super typhoon during 2018 PISTON field campaign. And so the model setup is listed here. Next slide.
Sue, please start wrapping up so that we have enough time for.
Yeah, I'm toward the end. Okay, so what they found, if you look at the civil pressure and the maximum wind speed, and so the track is showing on there. So the model is actually it's quite good. That follow the observed track pretty well. And what the conclusion is that they only see a small differences between the couple and uncoupled simulation. And so the result indicate that ocean feedback is not critical to Mengka. Probably is because the translation speed of Mengka is actually pretty fast. Now, next slide. Okay, so this is my last slide. So it's in summary. The PISTON modeling group was very productive. As you can see, that we conduct intra-seasonal predictability of the NGO, BSISO, monsoon and equatorial wave assessment. There are many studies on the land processes, the topographic effect, convection environment interaction, and air-sea land interaction. And with the observation data, we will continue to focus on the diurnal cycle. And because the PISTON campaign end up to be over the ocean, so more focus will be put on the air-sea interaction. And in conjunction with the PISTON 19 with CAMPAX, so there is also opportunity to look at the air cloud aerosol radiation interaction. And so all of that can lead to a very complicated model, multi-scale interaction. And most importantly is the model validation. So we can use the observation to help to understand the model biases. So the lesson learned from the modeling group. So basically, we have a lot of good results, so we learned quite a bit, but there are gaps that still exist in terms of the model synergy with observation. As you can see that all of the model study that most of them that we've done so far is really has a big part of land component. And then so because the modeling group hasn't been able to try to wrap up the previous work, we haven't started to look at closely at the air-sea interaction problem. And the second biggest problem is that there's a lack of the model data assimilation, observation impact, and the model verification study using the PISTON observation. And that concludes my talk. Thank you for your attention.
Thank you, Sue and Jim. I think maybe we can take one question for the audience before we go into the closed session. If anyone has a question, feel free to unmute yourself.
Okay, Jenny, if you can advance to the next slide when they are asked their question. So I would like to acknowledge, Jim and I would like to acknowledge our PISTON science team. Without the team effort, we couldn't pull off this 2 years of successful field campaign. And these are the list of the DPIs and the associates.
So I don't see any questions. Maybe we can just go directly into a closed session. Jim and Sue, do you have a little bit of time where we can have this discussion with the PISTON panel?
Yes, fine with me.
Yes.
Okay, great. So for those who are not part of the PISTON team or PISMIT panel, please kindly remove yourself from this Google Meet, and then we'll begin our closed panel discussion.
Yeah, sorry that took so long to get spun up. I think I must have not done something right. Google Chrome kept crashing every time I tried to present, and I didn't understand what happened.
Yeah, Jim, you're not alone. My Surface Pro crashed when you're trying to get in, and because it's overheating, so it's understandable. It never works sometimes.
All right, Kevin and Charlotte, you want to kick us off for this closed panel discussion?
Yeah, actually, I'm going to have to turn it over to Charlotte because I actually have to jump off. I have another scheduled call right at 1. So, Charlotte, do you mind kind of kicking us off?
Not at all. So I think I'll use this opportunity to sort of ask the first question. So I was sort of struck in listening to this talk that the importance of really small scale processes that or the potential importance of these small scale processes. So Jim talked about turbulent dissipation rates that were observed during the PISTON campaign. And so I'm wondering, how can these types of observations be used to improve models? How much is known about the representation of these turbulent dissipation rates in ocean models? And then secondly, from Sue's talk, one of the findings from, I think, Derek Posselt's work was the really rather profound effect of microphysics parameterizations can have and their impact on model skill. And so for Jim, I'm wondering how well are these turbulent dissipation rates represented in ocean models, if at all? And for Sue, what types of observations can be made to help better constrain models for their microphysical processes? So, sorry, that's a pretty detailed question, but I'll let you tackle that.
Should I go first, Sue?
Yeah, go ahead, Jim.
Okay, so I mean, this is what some of us spend our entire careers working on, is understanding how mixing is associated with the hierarchy of scales that cause the instabilities that lead to the mixing. And the formation of the instabilities is not quite clear. There are examples where we can represent the turbulence reasonably well. One example might be the diurnal warm layer, where the mixing is fairly well constrained by simple one-dimensional models. An example where we don't know how the mixing is associated with the instabilities very well is in association with wind forcing of the upper ocean, which presents itself in the form of acceleration of a jet in the mixed layer and the formation of near inertial gravity waves that propagate downwards and increase the energy below the mixed layer for extended periods of time after the wind forcing shuts off, and increase the turbulence disproportionate to the energy available in the near inertial waves. So I showed that example there as an example of something that we don't really understand very well. and it is not parameterized in any model. So that would be an example of things that we don't understand very well, and that hierarchy of fluid dynamics that leads to the instability, that leads to the turbulence, is not quite well understood either. And I noticed that one big effect in representing the MJO was an improvement in the turbulence parameterizations in the atmosphere. And that was one of the things, I think, one of the many things that came out of Dynamo.
Great, thank you.
That's a big topic, Charlotte.
Yeah.
Yeah, so may I chime in a little bit? So in
Sure,
terms of
please do.
the diurnal warm layers, so actually because of the turbulence, like Jim just described, the interaction with wind and the ocean turbulence is quite complex processes. And so really we need an ocean LES model to kind of help us to understand the parameterization issue, how you can combine the two and then maybe come up with some kind of parameterization for a model that requires subgrid scale parameterization to represent those turbulence.
Mhm.
Yeah, and I guess in recognition of that, PISTON does have an LES modeling component. Eric Skillingstad is involved in that. So I think we understand that there's a hierarchy of models that's required to represent these processes, at least approximately. I mean, of course, the problem with the LES is that things that are happening on bigger scales that you can't account for in the LES.
Right.
So it's all, this continues to be a hard problem.
Yeah, I totally agree, because the LES model is very expensive to run. And so the computation time is just incredible. So you can only represent a kind of idealized environment, but the real world is different. You know, there's many different environmental conditions that can actually drive the changes.
All right, let's see. I think Victoria has a question. Victoria, I'll let you go ahead or maybe just state your question or comment.
Sure. I was, I put it in the comment. I was just reflecting on the document that you guys sent around in advance. Very complete. Thank you so much for taking so much time with that. And one of the comments was the challenge, which I'm sure we've all come up against, of coping with different data formats and how to read and write all of the different types of measurements for the modeling teams. And I wondered if that might have contributed in some ways to the challenges the modeling teams have had in using the observations. Is this something that, you know, I feel like this is something that came up in other panels and webinars that we've had, and maybe this is something we should be thinking hard about.
Can I make a comment on that first, Sue?
Okay.
I think, so this experiment was based on a science plan that was a land, air, sea experiment. So the modelers got spun up doing the land, air, sea modeling in preparation to help guide the experiment. So they were focused on a different problem to begin with. So I think the biggest shortcomings that Sue might have mentioned were associated with the fact that we did a different experiment. And the data handling is always a problem, and Sue can comment more on that. But I think any disconnect is associated with the change of plan.
Yeah, so basically I wrote that answer. So because our group has been struggling to get all those different formats, you know, using all sorts of different tools we can get hands on. And so this is kind of, I think that in general in the science community, and partly that is probably is a coordination problem, that because the observation PI, they are super busy once they are on the field, and then afterwards they also are busy. Everybody is busy. We just haven't ahead of time that agree on a certain format that we can conform to. And so if there's a certain format or even a program that the observation PI can share with the team about how to read things. Just to give you one example is just actually Chris Farrell's team, the NOAA team, they actually, and the Elizabeth Thompson, they have done a wonderful job. And so they provide the Fox data, but they also provide some basic MATLAB script. So it's easier for us to just kind of read the data and see what they look like. And of course, a model needs a different format, but from there, it's just easier for us to figure out how to convert to that point. That's just one small example. Or the NetCDF, which is basically widely used in the science community. So some sort of uniform data format would be extremely helpful.
This came up in the T-Tides experiment as well. And I mean, we hear this often, and I just, maybe it's something that we should have put into our best practices paper, Janet.
This is a good point. You know, I think our community is pretty MATLAB centric or Python centric, and we don't use NetCDF as much as the atmospheric community does.
Yeah, so basically the modeling community is that sort of kind of moved toward NetCDF or HDF5 because models need to run on the supercomputer. And so model don't use MATLAB or model don't use Python. So basically it has to be that kind of format.
Okay, do we have some other questions for Jim or Sue?
Yeah, I would like, this is Antonietta Caputondi. I would like to ask a question to actually both of you, kind of is more like a general question. And being kind of a large scale physical oceanographer and climate scientist, from that viewpoint. So I think this campaign and what you have presented is absolutely fascinating in terms of really looking at these processes and also the modeling. I think most of the results seem to be kind of high resolution model of the area. So how do you think that this understanding of this region can actually be translated in improving also large-scale features and large-scale, climate and models that then are used for like predictions globally?
Shall I go first, Jim?
Go ahead, Sue.
Okay, so since our team is the only team that's actually used the global model, we're not quite to the climate scale yet. So maybe SPC is kind of doing the 45 days prediction, which is the intra-seasonal scale. Mm-hmm. So we have a look at this problem. And so so far, the result that I showed today is basically using the kind of satellite. We haven't looked into the PISTON observation yet, and that's why I'm saying that the PISTON data, of course, can use to understand the diurnal cycle very well. Because in the couple model, there's many sources of parameterization error, and because you couple, so your error actually propagate between the fluids. So that is true for climate model, especially important for climate model because the drift of the mainstay is it's a source of the climate prediction problem. And what we actually seeing in the from our own model, Navy SPC, that we do have a problem kind of capture the diurnal cycle precisely, especially over land and over the ocean, there is a phase shift. And so we suspect, and we haven't done a really detailed kind of things to sort it out, we suspect that the diurnal cycle error kind of propagate into the mean state, because you can imagine if you do 45 days forecast every day, your diurnal cycle is off. Of course, that depends on the phases. what's going on there, whether you have equatorial wave passing through, you have a BSISO, you have MJO, you have a monsoon. So it's quite complicated. But those errors can kind of accumulate daily. And so a small error can possibly lead to a bigger error by the end of 45 days forecast. And so the PISTON observations by the Western Pacific, I think will be really helpful in the long run to the community, because this is the area not a lot of located observation is available. And then because we were there 2 years, so captured quite a variety of different phenomena that's kind of away from the equator, especially under the typhoon. They were kind of really a surprise phase. So it's a great several cases as most ideal to actually look at the shallow cumulus predict problem in this area. And the shallow cumulus parameterization is also notorious hard in most of the model, and because model has to do the subgrid scale parameterization, so understanding is also very crucial.
And I guess just having that data set available for comparison to reanalysis products, something that Yolan Sarah from University of Washington is working on now, is valuable for just understanding how well those products represent the real world. So it's a test basis.
Yeah. But it seems to me that also like just understanding how the diurnal cycle, for example, can really kind of an incorrect representation of a diurnal cycle can propagate into maybe longer time scales or larger spatial scale problems. I think that in itself seems to be like something that we need to understand still.
This is Elizabeth. To interrupt Sue or Jim, I just wanted to say that NOAA just recently the Physical Sciences Lab and the Global Systems Lab will start doing some experiments with the UFS, so NOAA's global model. We're not going to assimilate PISTON observations, but it'll be kind of like sensitivity studies to understanding how well the PISTON region is represented in either reanalysis or initial conditions, and how that might impact downstream Western US precipitation, for instance. So that's one additional global model example.
Mm-hmm.
Yeah, so my feeling about so that's kind of just add on to what Elizabeth just said, that the gap that I mentioned, that we need more model to use this data, do a data assimilation, or even the ops impact. If the model has a 40 bar or HO model, they can do that. So you can look at either using the data denial, they can actually look at a lot of, see in this data buoy region, now you have this observation. Does it really help you prediction at all?
Right, yeah. No, yeah.
And Charlotte, I forgot to answer your question. Can you repeat your question again?
Oh, sure. My question was in relation to model prediction skill sensitivity to microphysical parameters. And so my question really is, what types of observations do we already collect, such as perhaps multi-parameter radar measurements, or what other types of observations would be needed to better constrain the microphysical parameterizations and models? This is a very small scale process that can impact things on a much larger scale, such as the formation of stratiform cloud decks that have a very widespread cloud radiative feedback impacts. So yeah, my question was about the microphysics.
Yeah, so PISTON actually is joined with CAMPAX. So from the CAMPAX side, they are interested in the cloud microphysics and aerosol radiation interaction. So actually, the CAMPAX does, my understanding, they have PIs that actually brought the microphysical instruments and then sampled the cloud during the PISTON 19. And so in terms of the model parameterization from Derek's study that indicate that the auto-conversion rate is that's the conversion rate between, where you're going to decide whether you're going to throw the things into the snow, ice, or rain, or cloud, that type of thing. So it's kind of like a sensitivity, there's some sensitivity in there. And so by comparing the cloud resolving models output of those with the probe, microphysics probe instruments about, the number of concentration and all those detailed things and the distribution, and that could actually constrain the model, the microphysics parameterization in some way.
Mm-hmm. Thank you. Let's see. I've been taking notes, so I haven't noticed if anyone has typed any additional questions into the chat. So let me see. I think I'll just ask, do we have any further questions or comments for Jim and Sue before we wrap up?
Yeah, this is Fred. I had a question.
Okay.
Several questions, but I'll just ask one of them. So I'm just interested a little bit in the history of this. So I presume that PISTON was planned to do certain things and answer certain questions, and the presumably proposals were submitted and funding was given out and all this kind of thing. And then you got rejected by the Philippine government twice to go in and do the field sampling that you wanted to do. First question is just out of curiosity, why did they reject your application? And second of all, I'm just wondering, how did you adjust your plans? Once you found out that you weren't able to really carry out the field campaign that you thought you were going to be able to, what kind of adjustments did you make into both the field activities and all the rest of the activities, modeling and so forth, that you were planning to do?
Yeah, okay. Hey, Jenny, can you go down a few slides? Keep going. Keep going. Oh, I think you're going the wrong direction, aren't you?
It's your slide, Jamie. Your slides is in the beginning of the deck, I think.
No, I put some extra slides after.
Oh,
okay.
Next. Okay, next. Okay, there's the reason for the denial of the MSR from the Philippines. So this is all we were told. So some political reason at a higher level than we are involved in. We were denied permission to work in the area, and I think all countries were. And it was unusual in the sense that there have been recent field experiments funded by the Office of Naval Research within the Philippines archipelago. So that was agreed on by the Philippines government. But at this point in time, there is some reason that the Philippine government has that they can't grant the application for an MSR. So I can't really answer why it happened. And people in the State Department were really helpful at trying to get this through, and they didn't really understand why either. So somebody does at some level that don't communicate with us. So that's the answer to the first question. And then the second question is, well, where do you go? Well, you don't have time to get clearances, so you need to go to international waters. We had a problem in the sense that we had pre-configured moorings that were already in the field, not deployed yet, but in sea containers ready to be deployed. So we had to find depth of water that would be compatible with deploying those moorings. We were stuck with the region of the Palau Ridge, which is claimed by as continental shelf by both Japan and by Palau. So we needed permission from Japan, which we got in 2 days. We made a request to Japan, they said yes. We made a request to Palau, and oh, could you go down a slide? There we go. We made a request to Palau, and it was granted a week before we were ready to deploy the moorings and had already been at sea for a month. And the method of conveying the permission from the president was by sending it to a local American who then sent me an email saying that we had permission. So it was done in a very unofficial way. We were prepared to do an air-sea interaction experiment completely. So we made that happen in international waters, and we made decisions on the fly that I think turned out to be pretty beneficial, but we just kind of made it up as we went along. I don't know if that's an answer or not, but that is some of the history.
That's good.
Okay. So in terms of modeling, we do, because like Jim said, we have a very little time to react. But it's for modeler, it's a little bit easier to kind of shift focus. So actually, we know there's a possibility that the MSR will be denied for 2018. And so we kind of organize all the PIs in PISTON, including the modeling group, so everybody chipping. So because it's on the Western Pacific, and in summer, everybody know that Western Pacific typhoon is a big problem. But it also presents a great opportunity to look at the air-sea interaction on the typhoon. And so, so there were many work that Jim and I weren't able to present because of the interest of time, that PISTON PI teams actually putting in the students to actually getting those climatology information about what's going on in Western Pacific during the time that PISTON's supposed to be there, what to expect, and then where's the best place to dodge. So we have a plan in place. You know, what happens if there's a typhoon coming? Where should we send the ship? You know, so we also have to shift all the modeling study within the PISTON team. The Columbia team, they were trying to get their couple models going, and of course we have COEMS and maybe ESPC, and so we shift our focus from South China Sea, Maritime Continent, to Western Pacific, and that's why one of the examples I showed them, my colleague, actually both Matt and Maria, so they actually look at the Western Pacific to see what's the predictability scale from the global model. And for COEMS, we done some study about the air-sea interaction, which I didn't have time to present on the Western Pacific. And so generally, those work, ballpark work from not just from the NRL group, but also from the other PISTON PI group, including the CSU, JPL, and then also Columbia. So we are kind of here to, shift the focus, and maybe now we have the observation data, we could actually kind of compare to see how model perform. And so for NRL team, we actually just finished a verification study to look at how the COEMS compare with using the PISTON sounding, and what are the model biases, and also the flux data we got from Elizabeth and Chris. And so we were able to understand where the model biases to come from.
Okay. Well, I think in the interest of time, we should probably try to wrap up here. I think if there are additional questions that we didn't have time to answer, perhaps you could email Jim or Sue directly. But I want to thank both of you for this really nice, thorough report on the PISTON project. It sounds like, just learning about the data that's been collected and the model experiments that have been performed has been really exciting and illuminating. So thank you both. And then Jenny, do you have any final comments before we wrap up?
So Charlotte, I have one more announcement that so the PISTON observation data are available on the NASA CAMPAX portal. And so it will be soon, sooner than later, that I think that will be released to the public along with the CAMPAX data.
Okay, that's great
Which
to know.
portal did you say? I'm sorry.
It's under the NASA CAMPAX,
It's in the
CAMP2EX.
It's in the report that we sent, Sue.
All right.
Okay.
Charlotte, thanks for the invitation, and it was a very nice discussion. Thank you.
All right. Thank you so much.
Thank you for the panels, the invitation, and thank you. And everybody have a nice weekend.
Okay.
Thank you.
So long.